The next thing we're going to talk about are functions. Now, in order to talk about functions, I have to give a definition for the more general case, and the most general case is called a relation. Now, a relation is any correspondence between x and y. Don't care what it is, doesn't have to follow any rules. It's just any relationship between x and y, and it's called a relation. A function, on the other hand, has specific rules that it must follow. A function is a relation, so that means it's a correspondence between x and y, and this relation means that each element in the domain, which is our x, must be assigned to exactly one element in the range. So I'll give you some graphics on exactly what that means. Now here we have a relation. I know it's a relation because there's a correspondence between the domain and the range. And in this correspondence, I need to check to see if each element in the domain only goes to one y. The 2 only goes to one y. The 3 only goes to one y. The 4 only goes to one y. And the 5 only goes to one y. So that must mean that this particular relation is also a function. So yep, this bad boy is a function. Now I'm going to adjust this just a little bit, and we'll see if the next one is a function. Here we have the 2 going to exactly 1y, the 3 goes to exactly 1y. Everything is the same except for the 5 goes to both a -2 and he goes to a -3. That means that this is not a function. And they'll do this to you with these diagrams. They'll do it to you with sets of numbers where they give them to you in brackets, and you have to check to see if each x only goes to one y. That's your criteria. Alright, here's some sets of numbers, and I'm going to check to see if each one of these is a function or not. So let's check the very first set of numbers. Alright, I'm checking to see if each x, the x's are 0, 1, and 2. I want to see if each x goes to exactly one y. And 0 is only going to a 1, 1 is only going to a 2. So yes, this is a function. Let me check the next one. I need to check to see if each x only goes to one y. 0 is only going one place, is only going to a 1, 1 is only going to 1, and 2 is only going to 1. So this is also a function. The next one, I need to check to see if each x, there's only one x, it looks like 0, and 0 is going to 1, 0 is going to 2, and 0 is going to 3. So this is definitely not a function. There's also something called the vertical line test. And in the vertical line test, you can look at some sort of equation that has been graphed to check to see if it passes something called a vertical line test. So we're going to look at that next. In the vertical line test, I'm checking to see if each x corresponds to exactly one y. And if this is the case, doesn't matter where I draw a vertical line, I will only cross my function in one place. And this one passes a vertical line test, so we will label him function. Now here's a familiar shape. I got a circle here. And this circle, I'm going to figure out if this circle is a function or not. So let's see. Does he pass a vertical line test? Whoops, I'm moving him around. He does not pass a vertical line test. So therefore, I'm going to say that this little buddy here is not a function, because right there and right there, he's going to cross. So we'd say that this little guy is not a function. Alright, Now we have this equation y equals 2x minus 1, and I did a little xy chart for you, and of course I could keep on going picking a bunch of things for x and then getting the corresponding value for y. And I might not be able to pick enough points to determine whether or not he was a function or not, but I can graph him and go, oh, look at the pattern of points. He's going to pass a vertical line test, so he must be a function. Now, we're going to do some other things with functions. We're going to put them in what's called function notation. And instead of writing y, I'm going to write f of x. And what this does is it enables me to be real specific about what the x is and what the y value are, because there's a lot of different x's and y's for this thing. So I would say that f of, and that's how we're going to describe this, f of 1 is equal to, and this is what x is right here, f of 1 means that x is 1. That's what that means inside that parenthesis. So I would replace x with a 1, and I would get that f of 1 is equal to 1 when I do that computation. I can look at my chart over there and tell you that f of 2 equals 3, because I've already plugged that in, and f of 3 equals 5. That's function notation. Now, carrying this over, I don't really have to put in a number if I don't want to. I could put in letters. I could say f of b equals, and then just replace x with b, 2b minus 1. I could get a little crazy and replace x with, let's say, x plus 1. And that means I replace x, anywhere there's an x, with x plus 1. And then I do the computation and clean it up because it's kind of dirty right now. So that's 2x plus 2 minus 1. And then I get that this equals 2x plus 1. And I can replace x with whatever it is that I put inside of here. It doesn't really matter what it is. They're going to give you all sorts of crazy functions, and they're going to say, compute this value, evaluate, something of that sort. All that means to do is take your function, and where there's an x, put in whatever it is they tell you to. So it'd be negative 2 times, put in a 4 for x, plus 1, and then minus 3. And you do this computation here. That would be negative 8 plus 1, that's negative 7. Minus 3, take the absolute value of negative 7, that's 7, minus 3, and this answer would be 4. So in this case, f of 4 equals 4. Well, that's kind of cute. Doesn't always happen that way where they're the same, but that was cute. Now these look really tough, but they're really not that bad if you just understand that this is what is called a piecewise defined function. So it's piecewise defined. And that just means that it's defined in pieces. When x is less than a negative 1, you use this little dude. When x is in between and equal to negative 1 and 1, the answer is just 4. Well, that's handy. When x is greater than 1, you just plug it into this guy. So for this one, my x is 0. So I go, which one of these little guys applies? It'd be the middle one. Like that one the best. That's easy. The next one, I'm going to have to do something. X is 3, so this bottom one here applies. So I'll just chunk the 3 in there for x and say 3 squared is 9. F of 3 is 9. The next one, x is negative 2. So I look at these three, see which one applies. That'd be this little dude up here. So I plug in a negative 2 wherever there's an x. And I get that f of negative 2 equals negative 7. And that's it for the piecewise defined. In some of your problems, you're going to be given something that looks like this. They're going to say, find all real values of x such that f of x equals 0. And that looks really scary, but just look at it and read exactly what it says. It says here that f of x equals 0. So f of x, right there, must be 0. So 0 equals x squared minus 9. Now find the x's that make this true. This one's sweet because he's a quadratic, but he factors nicely into an x plus 3 and an x minus 3. So when x is negative 3 or 3, then f of x equals 0. And I've done what they said. Alright, this word domain usually strikes fear into the hearts of math students. What domain means is, what can my x be? For the most part, your answers are going to be x is any real number. That's most of your answers. Another way to write this is x is an element of the real numbers. You can write it like that, or you can write it like negative infinity to positive infinity. Now that's if you just have a normal thing where you don't have any violators. Now here's going to come up with some violators. If I have, let's say, how about y equals 3 over x minus 2. Now most everything works for this except one thing. What doesn't work? Well, that would be a 2, because if I had a x equal to a 2, I'd have a 0 in the denominator, and that would not be allowed. So what I can do is just say that x is any real number where x is not equal to 2. So he's everything but 2. Let's see, another place that I have a problem is when I have something like y equals x minus 1. When I have square roots. When I have square roots, sometimes I'll have a problem because there's a whole lot of things x can't be. I can't have negatives underneath my square roots for it to be real. So I say, well, let me figure out if where x minus 1 is negative. The best way to do that is just say, well, where is x minus 1 equal to 0? Well, if he equals 0 at 1, then any time that x is less than 1, then he's going to be negative. So x needs to be greater than or equal to 1. And that would be your domain for this particular example. Alright, so you'll need to check in your denominators for 0. I replaced our example with what it is I need to do. And we need to check underneath our square roots for negative. These are the two places that you might have trouble and you need to check for. We are going to add to this list as we go on in the course because we're going to be looking at domain a lot. Now, just remember, for most cases, x is any real number. It's when I have x's in the denominator that I have to check for 0, and when I have square roots that I have to check to see if x could make this thing negative. Alright, and that's our function chapter. I think you should be able to do anything there, but if you have any trouble, because there's a lot of practice that's involved in this, if you have any trouble, just send me a message or get on the discussion board and I'll answer from there.